Hello students. Now let's move on to next theorem. If f is continuous on closed interval AB, then f belong to R of alpha on closed interval AB. So we need to prove that if any function is continuous on this closed interval, then it is Riemann-Stieltjes integrable on that interval. Now let's get into the proof. Since f is continuous on closed interval AB, f is uniformly continuous on closed interval AB. So we know that any function which is continuous on closed interval a comma b becomes uniformly continuous on that closed interval a comma b. So I have used that fact. Okay, and now using the definition of uniform continuity, I have for any epsilon positive, there exists delta positive such that mod of f of t1 minus f of t2 is less than epsilon by alpha b minus alpha a whenever t1 minus t2 less than delta. So here this is nothing but the definition of uniform continuity, and this holds for each and every t1 and t2 belonging to the interval. Okay, so here I have written epsilon by alpha b minus alpha a. Instead of writing epsilon, I have written this, and you will come to know why in the upcoming steps. Okay, and name this as equation 1. And since f is continuous on closed interval AB, it is bounded on closed interval AB. So any function which is continuous on closed interval AB is bounded on closed interval AB. Okay. Now let's see, if it is bounded, then there exists supremum and infimum. Okay. So here I have taken capital Mi and small mi to be the supremum and infimum of this particular interval. Okay, so here let f of t1 equal to mi and f of t2 equal to mi, small mi, for some t1 t2 belonging to this interval be the supremum and infimum of this interval. Okay, now let's choose a partition P of closed interval AB such that norm P is less than delta. We know what is norm P. See here, this is actually the maximum length of the subintervals of closed interval AB with respect to the partition P. Okay, and since I have chose norm P less than delta, then x1 minus x0, the distance between x1 minus x0, x2 minus x1 will all be less than delta. Why? Because the maximum length of the subinterval is less than delta, implies length of each and every subinterval is less than delta. So in general we write mod xi minus 1 less than delta for all I equal to 1 to n. So this holds for each and every I. Okay, so name this as equation 2. See, now I need to prove f belongs to R of alpha. So I need to prove the difference between the upper sum and lower sum is less than epsilon. Okay, so that is according to the condition of integrability. So what I will do, I will consider this difference. Then later I will prove that this difference is less than epsilon. Okay, so here according to the definition, this is equal to summation I equal to 1 to n capital Mi delta alpha I, and this is small mi into delta alpha I with the summation. So if I take this delta alpha I common, I have this. I will name this as equation 3. And also note that mod t1 minus t2 is less than delta, and this is from equation 2. Why? Because this mod xi minus 1 is less than delta for all I. And what is this t1 and t2? T1 and T2 belong to the subinterval xi minus 1 xi. So if the length between this is less than delta, so the length between any two elements, okay, any two elements in this particular subinterval xi minus 1 xi will also be less than delta. Not only the length between any elements in this particular subinterval, it also holds for these intervals also, as this is true for all I equal to 1 to n. So as of now, we have taken T1 and T2 from this particular subinterval. What is that? Xi minus 1 xi. So since the distance between this is less than delta, obviously the length between T1 and T2 will also be less than delta. Okay. And we have, see, whenever T1 minus T2 is less than delta, see, I have this. Whenever T1 minus T2 is less than delta, this holds according to the definition of uniform continuity. So, if I use that, okay, see, if this holds, then this holds from equation 1. That is according to the definition of uniform continuity. So, mod of f of t1 minus f of t2 is less than epsilon by alpha b minus alpha a whenever mod t1 minus t2 less than delta. Okay, and this is for all I equal to 1 to n. Okay, see, because it is actually, I have used the definition of uniform continuity, so this holds for all I. And here actually I have taken f of t1 as mi and f of t2 as a small m. Okay, so here actually mi and small mi is the supremum and infimum on this particular interval. So there exist two elements in this interval such that f of t1 is equal to mi and f of t2 is equal to small mi. So in place of f of t1 I have capital Mi and f of t2 I have small mi. Okay. So in place of f of t1 I have capital Mi and f of t2 I have small mi, and this is less than epsilon by alpha b minus alpha a. Okay, and here this from equation 3 I have this is less than epsilon by alpha b minus alpha a. So I will use this equation 4 in 3. So that becomes like this. See, 3 implies u of p comma f comma alpha minus L of p comma f comma alpha less than, see, I have also taken this epsilon by alpha b minus alpha a outside the summation, as this has nothing to do with this summation I equal to 1 to n. So I have done this directly. So this has come out of the summation and you have left with summation I equal to 1 to n delta alpha I. Okay, and here this actually when you expand this summation you have alpha b minus alpha a. So now you can cancel alpha b minus alpha a here, and that is why you have taken epsilon by alpha b minus alpha a instead of only epsilon, so that this will get cancelled and at last you will get epsilon. Okay, so u of p comma f comma alpha minus L of p comma f comma alpha is less than epsilon, and if this is less than epsilon for any epsilon positive, then this f belongs to order of alpha on closed interval AB. And also you have to note this point, the converse of the above theorem need not be true. That is, if f belongs to R of alpha, then f need not be continuous. Okay, so if every function f which is continuous belongs to R of alpha, but the converse is not true. If f belongs to R of alpha, then f need not be continuous. There exist some functions which belong to R of alpha and still they are discontinuous. Okay, so that is all about the proof. Thank you.